As telco edge services start to become a reality, what should network operators be doing to ensure they can deliver the services that customers will actually want to use? Well, I'm talking today with Dominik Schnieders, Head of Edge Computing and Cloud XR at Deutsche Telekom, about this topic and about Deutsche Telekom's edge computing and services strategy. So, Dominik, can you give us a quick update on Deutsche Telekom's edge services strategy? Are there any milestones or new areas of focus you can tell us about?
Yeah, thanks a lot for the invitation. I'm very happy to be here today. I've been working on edge computing now personally for 3.5 years, and it's a fascinating area with a whole opportunities on use cases. And we had great achievements in the past, milestones there. Just to mention them, we built 5 edge data centers in Germany on productive network to use for our customers. And we founded a company called Mobile Edge X. It's a company for an edge platform as a service. When we come to the new milestones or the focus area, I would like to point out a few of them. So first one is Mobile Edge X is now engaged with several corporations and contracts in the telco industry. That's a really good progress there. And secondly, we were in a phase on edge computing, as it's still a young technology, where we did a lot of POCs, and we just moved to the first commercial contracts with our customers. That's also a big milestone for us, and it's good for the progress of edge computing. Additionally, the last years, we had close cooperations with other operators within the GSMA, but let me mention maybe one of the cooperations that we had explicitly. It was with Telefonica, and it was an AR use case, an AR game, and you can watch that also on YouTube. It was an AR game between our two networks. So the players were in the Telefonica network and the Deutsche Telekom network. We used Mobile Edge X as a platform, and we worked together with a company called Slavic Monster for that game. That was excellent, and it showed that this collaboration also works between different operators. Additionally, we're working with Telefonica on a POC together with Continental and also Mobile Edge X in the context of automotive use case. It's a collision avoidance warning use case. And here it's also important that we are able to exchange information very quickly with a low latency between two different networks. Last one, which we will also touch today, is about we were able to improve and work on improving the network latency. So besides edge computing, our network is the second part for that, let's say, end-to-end network latency experience for a customer. It's crucial that we improve also the network latency.
Okay, so a lot going on there. That's great news. Now, there's been a lot of talk in the past few years about how edge computing will enable the development and delivery of new revenue-generating services, such as AR, VR, cloud gaming, remote control applications in industrial settings, and much more. Is there any evidence of customer demand for such services?
Definitely. I'm personally very much engaged with a lot of companies in that area. It's about in the cloud gaming area. It's about remote rendering for AR, VR applications. It's about offloading of object detection, for example, for cars, for AGVs, or for drones. So all that do that object detection on the edge cloud. And another example is teleoperated driving. And actually, we built around 50 POCs in the past in all of that areas. What we see is that there is a clear use case demand. These use cases, they need low latency, they need edge computing. And actually, the requirements became really clearer what exactly they need. And if I would summarize that, what we need to improve is the performance of edge computing, especially together with our networks, to deliver a very good latency to these use cases. And the demand is there. So what we need to do is improve a little bit on our side, work together with these companies and unlock these latency critical use cases.
Okay, so the use cases are being developed, the demand is there, but what about the technical aspects of enabling such services? What are the key metrics? It seems that low latency really is as important as it seems.
It is so important. edge computing is offering different kind of properties of capabilities. It is, for example, privacy and security. With edge computing, we can improve that. In principle, edge computing is about decentralization. So what we do is we bring with our edge computing, the compute closer to the devices. And with that, we can also compute the uplink traffic earlier at the edge and can avoid that there's a traffic going through the entire network somewhere to the internet. So it's about, let's say, keeping the traffic low on the backbone and do the compute decentralized. That's all edge computing. But if you would ask me, what is the basic one? What is the one that really drives most of our customer? We will come back to that one about low latency. It's the most important metric, at least what we saw from our engagements with our customers. So the low latency aspect is the one that we need to enforce for edge computing.
Okay, so what advances can be made to enable low latency connectivity?
So what we learned out of the collaboration with our customers is that low and especially stable latency in the network is essential. Let me explain a little bit with the example of cloud gaming, as for example, Magenta Gaming, what we as Deutsche Telekom do, or Google Stadia, NVIDIA GeForce Now. The idea of that cloud gaming is to offload part of the computation to the edge cloud. For example, that would be the game engine that runs then on the edge and where the scene is then brought together, computed. And additionally, also the rendering takes place on the edge with the GPU. So we offload part of that really complex computation to the edge cloud. And with that, keep the end device simpler. It's just an input device as a gamepad and it's a display. That's essentially what you need for cloud gaming. But what you get from that is additionally that you are depending on the latency. And you can imagine that you push a button on your controller for any kind of input, and that's sent over a mobile network to the edge where all this computation takes place. And then just a video stream gets back. So if there is a latency that's too high, you will recognize that your input as delayed to the output that you see, and the system reacts too late. Actually, looking into that aspect of latency, there are two aspects. And the one aspect we mostly talked about, it's the average latency. So it's the principal reactiveness of the system over a longer time. But there's a second aspect, and that's even more important. Additionally to that average latency that needs to be in the right ballpark, it's about the stability of the latency. And I give you another example. If you play a game for some minutes, for example, a race on that cloud gaming or a shooter, and everything is fine in terms of latency, but at some time, there's a latency spike of a few hundred milliseconds. And this lasts a few hundred milliseconds or even a second. So latency is high and your packets are delayed. What you will experience is really a lag in your gaming experience. And as a gamer, you will maybe say, okay, if it happens once or twice, that's okay. But if that happens too often, you will very probably say that it's still too immature and you can't play that over a network. So cloud gaming doesn't really work. And for that reason, it's important to also stabilize the latency. And if I say stabilize, it's about having some kind of low jitter, a low deviation from latency, or some kind of upper bounded latency. So latency shouldn't be above some kind of latency values in order to be still able to play. By the way, jitter is most recognizable if you have a very low average latency and then you have a high one. This is really something that additionally you recognize. So if we would summarize that, first of all, the average network latency, that is something they experience over a longer time, and it needs to be in the right order of magnitude. But what we really need to focus on is a low jitter and, as said, that upper bounded latency to really unlock that latency critical use cases. We call that managed latency, that upper bounded latency. And if you look where most of the latency and especially the jitter will come from on a mobile network, it is the radio access network. That's the the air interface between base station and device. It's in the nature of that because it's an air interface, and you need to share that spectrum between different users. You have different, also partially very demanding cell conditions, for example, if you have cell edge or if you have mobility. So most of the jitter is deriving from the radio access network. And for that reason, when we recognized and learned that two aspects about the latency, we said, okay, let's start a cooperation. And we did that cooperation together with Ericsson to see if we can find a solution for that problem to get a managed latency. And actually, we developed that with Ericsson now for some time, and it's a solution for high bitrate, low latency applications like cloud gaming. And one of the methods that we use there is called L4S. L4S stands for low latency, low loss, scalable throughput, and it's based on an IETF standardization. So focusing on that managed latency is essential to really help the latency critical applications.
Okay, that sounds interesting. Can you tell us a bit more about managed latency with low latency, low loss, scalable throughput, or L4S?
Yeah. So it's embedded in an overall system. First of all, it's not easy to achieve low and stable latency in a radio access network on the air interface between base station and UE. What you need for that is prioritization. And we know that way of doing it from very famous use case, voice over LTE. With voice over LTE, we apply a prioritization for our packets for transmitting the voice data. If we wouldn't do that, these voice data would be totally treated equivalent to, let's say, YouTube, and any kind of, let's say, latency and jitter would impact your audio quality. So what's clear, we need to prioritize. But there's a main difference between voice over LTE and the use cases we talk about. Voice over LTE is using a very low bit rate. It's around, depending on the codec, 12.5 kilobits per second. And for that reason, you can prioritize that in a network and it doesn't harm the other users. If we talk and look about our use cases, about these edge use cases that are the main ones, it's something like cloud gaming, and they demand something between a few Mbits per second and a few tens of Mbits per second. And here you can't simply prioritize. So besides that prioritization, there needs to be something else in order to make that system work. And that's exactly what we thought of a lot in the past and found out a way forward for that. What we learned was you need to have some kind of feedback loop from the network back to the application. And that feedback loop will give you an information directly out of the network about the congestion status in the network node. And if we have a very quick feedback loop, the application can do rate adaptation, which then in the end is essential to have a low latency. So let me explain a little bit more in detail. What we use for the feedback loop is that L4S based on an IETF standardization. L4S is a technology where you can mark packets in the IP header. Marking packets simply means that you have you set 2 bits there, the so-called ECN bits. And with that, you can indicate that there's some congestion. So if you imagine you push in more into the system, a higher bit rate, then your radio is capable to transmit on the other side. The packets will line up. That's exactly latency and jitter. That's what's happening all the time. And what we do there, we mark if the RAN or any other network node sees such a congestion, it starts to mark these packets. These packets go on to the client, back to the server side or the sender side. And with that information, it's a proportional marking. The more congestion, the more the packets are marked up to 100%. The application can do rate adaptation and adapt to that, let's say, input equal to the output, the possible output. That's it. Prioritization, fast feedback loop, including edge, and rate adaptation. If you look at it in other words, we could say today the network is some kind of black box. All the application, YouTube and all the rest of the applications, they send something in and something happens there in the network, and over the top they try to find out what the network does, what happens there. They do rate adaptation from outside, but it's slow, and it doesn't matter because YouTube or Netflix, they buffer on the end device the packet. So if there's any congestion, a short one, a few hundred milliseconds, that doesn't matter because on your device side, the buffer just will go down a little bit and then will fill up again. And overall, they do rate adaptation. So they know about rate adaptation. What is missing is that insight into the network. And that's exactly what we will give them. We will give them information directly from the heart of the network about the congestion status, so they know exactly what kind of bit rate they need to apply in order to get the input into the network equal to the output. That combined with prioritization gives you an excellent latency and especially a stable latency. As said, we developed that and tested that with Ericsson. We tested it now for the last 3/4 of the year intensively in all kind of network conditions. That's essential to really try out cell edges, mobility, all these, let's say, more difficult cell situation where you usually see that latency spikes, that jitter. And I can say that it really works very well. We achieve a low and we especially achieve a stable latency with an upper bounded latency. That's essential. And we just published a white paper on that around 2-3 weeks ago. And it's really open. And I just want to mention that it's about an open approach based on a standardization for everybody to use. It's essential to have that at scale. Just a few words now on this prioritization, fast feedback loop, and rate adaptation system, managed latency. First of all, it's very efficient in the use of the resource of the spectrum. And that's necessary because also fairness needs to be fulfilled. If you prioritize, just simply prioritize, you could take away a lot of spectrum from the other devices. And that's not good for their experience. So with our approach, it's a very fair approach. And it's a very efficient one that fulfills the target. In just 2 sentences summarized from a radio expert that described it, he said, in order to achieve low and stable latency, you need to do prioritization. But in order to prioritize, to be able to prioritize in a network, what you need to do is rate adaptation, and in brackets, with a fast feedback loop from the network back to the application to do the rate adaptation.
Okay, so this sounds like a really interesting development that can help to push edge services along. Is Deutsche Telekom doing anything itself to advance the development of managed latency? And are you working with any specific partners on this?
We do. As said, we developed that approach of managed latency together with Ericsson. We just published a white paper describing in depth and totally open how it's done. Important to notice, it's based on an IETF standardization. Additionally, this link to IETF standardization was just brought into 3GPP, also to have that close relationship to 3GPP of that approach. And actually, we are talking to a lot of other network suppliers, but also operators, to the operators, in order to share that. It's about an absolutely open approach based on standardization that can be and should be hopefully used worldwide in the end, as it's essential to really get that benefit from edge computing together with the network and get the best for our customers. And last but not least, of course, we try that out with customers. So we, as said, we were very much engaged with prototypes on the edge computing side, and we're just trying also and pushing that approach with managed latency and edge computing forward with our customers, together with our customers.
Okay, excellent. Now, what would you like to see the industry focus on next in terms of telco edge R&D?
Of course, edge is the center also from what I'm doing. But besides edge, we should enforce that network optimization, as it's key for an end-to-end latency experience for our customers. Managed latency with L4S is an excellent way to manage it. For example, in the radio access network, which causes most of the causes most of the latency and jitter. But you can also use L4S in other network nodes. So it's about improving our network latency experiences. And it fits very well also in slicing. So this can be super nicely integrated in slicing. So one part of it, I would see that we as an industry should see that we improve network latency stability. And of course, additionally, push on for edge computing. Edge computing in combination with an optimized network latency, that will bring this low and stable latency to our customers, which they really require in the use cases which you asked in the beginning. That's exactly what they want, low and stable latency. And if you combine that, if we have a super good network with managed latency with L4S, including or building onto slices, and we combine that with edge computing, we can really fulfill the customer demand. And with that, enable really new innovative use cases for our customers, help them to get them and realize them.
Great. Well, Dominik, it's been great to talk to you today and to hear about what Deutsche Telekom is doing and the advances in managed latency. Thanks very much for joining us.
You're welcome. It was a pleasure. Thanks.